Hey, it worked. Hi, it's Miss Murphy. So today we're going to get into something that's a little bit more tricky. It's actually not tricky. It's just for me to teach it. I'm going to try to be a little bit more savvy. Okay. Today we're going to talk about mass spectrometry. Sometimes it's also referred to as mass spectroscopy. Either way, it involves isotopes, their individual masses, and their percent abundances. And it's very simple. Okay, so let me first share my screen here with this. I'm sorry, I was thinking. I'm going to go to my desktop. Okay. Curious. Okay. So you should be looking at what I'm looking at, which is our Unit 1 PowerPoint. Please excuse my name, Coronavirus Unit 1. I made these when at the end of the school year last year because I had to rearrange all these units. Anyway, what we have here is overview of mass spectrometry, also referred to as spectroscopy. And this is a rough diagram of a mass spectrometer. In an experiment as such, a sample is ionized where it produces ions, so they remove electrons from it to produce positive ions. The ions separate into smaller ions, all of which are carried to a detector, blah, blah, blah. And what this does, this detector here, I'll go through this in a minute, gives a mass to charge ratio, okay? So you put your sample in matter in here, a pure sample. Actually, they're not always pure, that's not true. The particles, and for us, it's going to consist of atoms, get ionized, right? Ions accelerated. Here we have a positive. This would be actually the negative side. I know that. And I'll explain to you in a minute. And this would be the positive side. And what we see is that these ionized particles are being separated based of their mass, such that the lightest particles are deflected more. And that makes sense because it's easier to pull something light to you. Now remember, these are ionized into cations, right? Right here. That's how I knew this was negative, because it's attracted. There, if this is positive, I could easily infer that this must be negative. Okay, so that's it. You really don't need to know much more about that. All the different particles hit here. We can use the angles to determine the mass to charge ratio, but we do not have to do that. So that's left to people above us. Not above, but different coursework, not what we're looking into. So this is what you need to be really, understand, is that what comes out, the relative mass to charge ratio, these should be labeled. This should be atomic mass units down here, the mass, the atomic mass, NAMU, atomic mass units. And you see here that this is abundance, okay? Notice it is a relative, so this, okay, I don't want to get into that. This is going to be your abundance. Usually it's a percent abundance, okay? However, this is the mass spectrum for boron. Well, let me tell you what I noticed. I noticed there's one line. Unless that's, okay, that makes more sense now. This is supposed to be a line as well. It's just not as dark. That makes more sense. Now I can go back. Notice that this says, I was confused. This says relative abundance. That's why this goes all the way up to the 100, while this is sitting down here at, like, I don't know, 20 or 30 or something. Notice that, okay? Because it's not percent abundance, which most often it is, but rather it says relative, these do not have to add up to 100, okay? These are relative, right? Relative to 100%, he hit here. Usually they are percentages. If they were percentages, we would expect these to add up to 100. But what else I notice is there's one line at the 10. So each line simply represents an isotope of boron. And because there are two lines, there are two isotopes. One weighs 10, looks like one weighs 10.5, which also does not make sense to me right now. I'm assuming that is a line. That does make sense to me. So I can tell that there's two isotopes. This one here, okay, it does make sense. This is not 10.5, this is 11, because look, it goes 4, 5, 6, 7, 8. Silly Miss Murphy. This is 11, perfectly good sense. I'll tell you why. Because the average atomic mass for boron is 10.81, I believe. So if we were to take this and include its abundance, and take this and include its abundance, we see that the average would come right around here, which is about 10.81. So from reading this, I could see that boron has two naturally occurring isotopes, and that boron's average atomic mass, the one that's located on the periodic table, should lie right around here. Definitely much closer to this line because he's so much more abundant than this line because he's less abundant. Let's scroll down. Okay, immediately what I noticed it's still, I'm not appreciating that, relative, and that doesn't go there. I can't see the whole thing. That's got to be a percent here. It's got to say percent right there because these look like they would add up to 100. That's okay. What I notice most importantly is there's 1, 2, 3, 4, 5 naturally occurring isotopes for zirconium. Zirconium has 5 isotopes. I see that this one is the most abundant, and this one here is the least abundant. And the average abundance should lie probably somewhere around here, right? It's going to be closest to the most abundant, but you see these are going to pull it down quite a bit. Okay. Now, let's see what we have here. Actually, oh yeah, I was going to do that. Here's a question. How many isotopes are there? Well, 1, we just looked at this, 2, 3, 4, 5. How do you know? Because there are peaks at 5 different atomic masses, right? This is your mass per charge. What do the relative heights of the lines give you? They relate to the percent abundance of that isotope in nature. This tells me that most of my, I believe this was zirconium, atoms have a mass of 90, and a lot of them have a mass of 94 and 92. Very few of them have a mass of 96 and 91, a little bit more than 96, and most of them have a mass of 90. That's what it tells me. It also tells me that the average atomic mass should lie somewhere within this region. What is the average atomic mass? Well, let's calculate the average atomic mass. We know how to do that, right? We know how to do that. Let's go like this now, and let's calculate that average atomic mass. And what I'm going to do real quick is I'm going to write those numbers down. We had 90. I'm writing them down. I'll be back in a minute, and I will have them on my screen. I know this is very ill-effective. 51.1, 11.2, 17.1. It's not a perfect world. 17.4. I've learned to accept it. You must as well. I'm on my way back. I just need to find where you went on my computer. And I think I remember, and I think I just closed all that. Yep, I found you. Okay, here we are. I'm back. Hey, let me make this big, okay? So what the question said was, what element is this? And these were the average atomic masses that they gave us for each of the 5 isotopes. And these were the percent abundances that we were given for each of the 5 isotopes. And in order to determine what element this is, I'm simply going to calculate the average atomic mass. And I'm going to find that element on the periodic table by way of his average atomic mass, and I'm going to identify the element. Okay? So remember, in order to do that, we are going to take the mass of each isotope, which is the first number. Sometimes they're in decimals. These are whole numbers. We're going to multiply that by the percent abundance. We are going to, and we're going to press equals. What we are not going to do is we are not going to add these up and divide these by 5. That would be absolutely the wrong thing to do. The average atomic mass is a special average, and it has nothing, you do not ever divide by the number. So I'm going to clear this. I'm going to do 90 times 51.1 divided by, no. I'm going to add that to it. Plus I'm going to add all these up together. Actually, let's just go like this. Delete equals 459.90, 4599, 91 times 11.2 is 1019.2. 92 times 17.1 equals 1573.2. 94 times 17.4 equals 1635.6. 96 times 2.8 equals 268.8. I'm going to add all of these up. Okay, let me get this out of my way. All I did was multiply my average atomic mass by my percent abundances. I'm now going to take the last number and add 1635.6. Personally, I would have done this all at the same time if I wasn't teaching, but I would be cautious to not make a mistake because I'm very prone to mistakes. I got 9095.8. That is, I need to divide that now by 100. And I get 90.958 atomic mass units. Okay, or right at 91, right? It's also right at 91. Sorry about that, guys. Atomic mass units. Now, if we, those of you, you could also, if you wanted to, you could go ahead and divide this by 100, and then you would have gotten this. You could have divided this by 100, and you could have done that all the way down. That's the way I teach my kids often. And you would have already ended up with that number. Okay, so you can either do it each individual step, or you can do it one time at the end. I actually usually do this blue way, but it doesn't matter. Now, I'm going to go back to my computer screen, and we're going to go look at the periodic table. Okay. Let's look at the periodic table. Sorry. Shoot. Wrong button. There we go. Share. Oh my goodness, I think I closed my stuff out. I didn't, yay. And I have a periodic table pulled up right here. I think right here. Yeah, and if you look right here, 91.22. I mean, we got 91, but my guess would be that was zirconium. There's no under there 91, and we definitely got 91. You know, it's usually pretty right. It's pretty right on. It's not perfect, but I'm not worried about that right now. I think you see how to do that. Now, let's look here and how some of these might work. So, you know, briefly explain how a mass spectrometer works. Well, right, it basically ionizes a sample and then separates the different particles based on their mass, right? By having a magnet, and the ones that are lighter are deflected more. And then, you know, someone does some fancy stuff to figure out a mass to charge ratio, right? Okay, an element is composed of 3 stable isotopes, A1, A2, A3. Gives us our percent abundance for each. And we are asked to draw a mass spectrum of that element. Notice that we have percent abundance. We're going to get the atomic mass, and then we're going to answer a couple questions. So let's go back here. Man, I should probably make you do that yourself in class. I guess I'm going to let you get off this time. Okay. I don't know about that. That might be a really good classroom activity. I think I'm going to leave that for the class. So, my friends, that is average atomic mass by mass, and actually more mass spectroscopy. Okay. So the mass on the periodic table is what we got from the mass spectroscopy. Spectrometry, you can go either way. Probably spectrometry might be more relevant. And I'm not going to go over that last question. I'll let you think about it. All right. See ya.